we're back today and we're going to be solving ODEs, PDEs with engineering examples. So today we're going to focus on, and actually in this series of lectures we're going to focus on how do we solve ODEs, PDEs using Mathematica, how do we set them up, what's the correct syntax, and then we're going to use a whole host of basically Mathematica suites that are going to allow us to solve these ODEs and PDEs generally, specifically, numerically, and then the key thing that we're going to focus on is not how to solve them mathematically with our hands. Again, that's why we have Mathematica, but instead how do we set up initial condition, boundary conditions to match the physical input of our system. So let's go ahead and move forward. So let's go ahead, we could solve, again, this ODE is what type? It is an ODE because I'm only looking at one partial derivative. It is first order. So I can solve for this general solution, and I can see because it's first order, first derivative, we need to find a boundary condition. So boundary conditions are different from initial conditions. Boundary conditions refer to space variables. So we need to specify initial conditions. So we're asking here in DSolve, this is my function, and then solve this ODE, PDE, whatever we're looking for, as a function of this function with these variables. If I want to specify an initial condition or boundary condition, I say in brackets here, I have my ODE, set my initial condition, and then evaluate this function as a function of x, and we get a trivial solution. You could also specify other variables here for 4, and we get, again, a non-trivial solution. You could also specify time derivative here, and you can get a solution as well. Or we could say this must be equal to 0, we get that, 1. Again, you get the picture. So you could kind of change these values. You could do inhomogeneous first order ODEs. And again, we see here first order 1, so we see one constant, and we could solve for this. Again, just as we did previously here. So I'm going to set my things here, and I'm going to set my y prime 0 equals 0. Let's find the solution. Ooh, it does not like that solution. How about y prime? Oops. Oh, see here, I need to set that double equal sign. So let me clear, actually, I can quit my kernel here. Quit the kernel. And then I can solve this one. So make sure you use that double equal sign. And here it still doesn't like it. So you can sign here, empty solution. How about y prime 0 equals 1? You can start to see some values here. We can do 5. Again, you can start to solve. That was an interesting solution. So 1 gives me something. But anyways, we could solve for those values now. So, or actually, I can even set this value here. You can do second order. So second order ODEs, you see I have 2 constants, so I need 2 boundary conditions. So I could do here, I could do y of 1 equals 2, solve for that. Again, I just need 2 boundary conditions to solve this ODE here. Again, similarly here, get my function, and I could solve more complex problems. I could do third order ODEs generally, so again, you could see constant 1, constant 2, constant 3 here. You can solve systems of differential equations if you would like to. Again, specifying boundary conditions on each of them. You can solve first order PDEs, multiple variables. We'll be looking at these functions very soon. Hopefully they remind you heat transfer, diffusion, mass transport, kinetics. We can do just various functions here. Nonlinear ODEs or Ds, as you can see here. Again, constants, and then a general ODE. Hopefully, this is your basically your Schrodinger's equation. And we'll take a look at this guy in one of our example problems in our in-class activities or in our problem set and in our problem sets. All right. So that's generally how you solve ODEs, PDEs using Mathematica, using DSolve. So next time we're going to get into numerically solving ODEs, PDEs, differential equations. See you in the next video. Thanks. Bye.